Hi everyone, in this video we are going to discuss efficiency. And so the best way to do that is just by looking at a video of Newton's Cradle. So we'll start off here. Ooh, so fancy, right? Have you guys seen these before? Hopefully. And so now, if you want to amp it up a little bit, you can do two at once. Ooh, how cool, right? But the important thing we need to see is that it eventually stops at the bottom. Okay, so I'm not going to make you keep watching this, but let's talk about what we just witnessed here. This is Newton's Cradle. First things first, if you ever have a nerd professor or friend, they love these gifts because there's so much physics and chemistry in there, so just a little inside note. All right, so here we go. Have Newton's Cradle. You have 5 balls here. You pick one up to the top. The one that you're holding at the top has insane potential energy. It's high up from the ground. It's not moving, so it's just potential energy. The second you let go, it starts moving, so the potential energy has been transferred to kinetic energy. So kinetic energy until it hits the bottom. Other balls over here. So then boom, kinetic, all the way up to the last one. Where you hit the last ball, it transfers all the way up to the top. Kinetic energy until it reaches its maximum height. So then you're at the most potential energy again, and then drops back down. And so potential back to kinetic, moving, hitting it. Kinetic, all the way back up. And it goes over and over and over again until eventually it gets to the spot at the very bottom where it stops moving. So here is my question. How is that possible considering the first law of thermodynamics? Now, we said that the first law of thermodynamics is just saying that energy cannot be created or destroyed. So energy must be transferred. So the reason why I'm talking to you about this is that energy is lost as heat or sound. And so we could hear the sound from the video, the little every time the balls hit each other. But after a while, if you were actually able to touch that system or touch Newton's Cradle, you would actually be able to feel that heat energy or that thermal energy that is transferred when every time those balls are knocking into each other. So now, why am I talking to you about this? Well, it turns out that the same type of process occurs in a power plant. And so no power plant, not one out there on this planet, is perfectly efficient so that they could transfer the potential energy into kinetic energy, into mechanical energy, into electrical energy, which is then brought out into our earth or to the system so that all of us people out here can happily have electricity or play with our Xbox or whatever it is that we want to do. The problem is these power plants lose energy as heat. Okay, so they're not efficient. So we use the term efficient to actually say how well do we transfer this energy all the way from the combustion of the coal all the way to the very, very end where we're releasing electricity out into the environment or out into people's homes and whatnot. I don't want you thinking of electricity going out in the atmosphere. It's on a specific route. So what we need to talk about now is something called percent net efficiency. So this is an actual term that we talk about. Super important, and it has a very specific formula. So it is just a ratio of the actual electrical energy that is produced at the very end of the system, and we do this over the heat from the fuel. So essentially, how much heat energy was released during the combustion of our fuel, if it's coal, okay, so how much energy is released when we burn coal relative to the amount of energy or electrical energy or electricity that's actually produced at the very end. Now, we always do this in terms of percent, so times 100. So that's one way of calculating net efficiency. Another way of doing that would be to separate everything out into its specific steps. So we could talk about the combustion of the fuel. We could talk about the heating up of the water in the boiler. We could talk about the spinning of the turbine and then in the generator. So let's say, for example, that this power plant has 4 steps. So our percent net efficiency would just be equal to the efficiency of step 1 times the efficiency of step 2 times the efficiency of step 3 times the efficiency of step 4. So they're all multiplied together. So in real life, power plants have a net efficiency of anywhere between 30 and 50%, which is deplorable. I mean, that is so bad that we're losing all of this heat energy. So we're burning all this coal, releasing all these pollutants into the atmosphere, way increasing our carbon dioxide concentration, only for 30 to 50% efficiency. And actually, just to give you a number that's even more depressing, in the US, our efficiency has been on average 33% for 4 decades, and it has not increased, which is really sad. All right, so let's see if this makes sense to you guys. A coal plant with a net efficiency of 38% generates, we're going to have to do some math here, guys, 5.0 times 10 to the 12th joules of electricity per day. So we're going to say this is daily. Now, how much heat energy was produced in the boiler? Okay, so using the information we just had, we have a 38% net efficiency. We know we're generating 5 times 10 to the 12th joules of electricity per day. Now we want to know how much heat energy did that come from originally. Go. All right, did you get an answer? Hopefully you did. All you had to do is set up a very simple mathematical expression. So we said that our efficiency was 38%. So 38%, that's on the left side. We set that equal to the amount of electrical energy that is produced. So that would be 5.0 times 10 to the 12th joules. And that is all over our heat from our fuel. So that's what we're solving for, our heat at the bottom. And then this is percent, so we're just multiplying this times 100. So all you had to do was 5 times 10 to the 12th divided by 38 and multiply that number times 100. And we end up with our heat energy as 1.31 times 10 to the 13th joules. Okay, so this is how much energy was released when we burned a bunch of coal in one day at a power plant. Okay, that's a lot of energy. You think about how much of that is released out into the environment as carbon dioxide or as pollutants. It's a big deal, right? All right, so now here's my question. If this much was burned right here, how much energy was lost as heat energy? So during this transformation, how much was actually lost? Go. All right, did you get an answer? Hopefully you did, and it was a lot simpler than some people like to make this seem. So all you have to do is take the amount of heat that was originally burned, so the 1.31 times 10 to the 13th joules. We're subtracting it out from the amount of electrical energy that was actually produced, so the 5.0 times 10 to the 12th joules, and we're just taking the difference. And if you did that properly, you should get an answer of around 8.1 times 10 to the 12th joules. So this is a lot. That is a really, really big number that is lost as heat energy. So we create this much energy per day in every single power plant, and it's just gone. It's released out into the atmosphere. We don't do anything with it. So our power plants, not only are they destroying our environment in terms of the air we breathe, so the pollutants, and then also our carbon dioxide levels, so we're increasing our temperature of the planet, but we are also not even doing it properly. We're not using it. We're not even efficient with this. We're losing all this energy. We need to find a better way. Okay, off my soapbox. Bye, guys.